Hi everybody, in this video I'm going to be talking about function transformations using horizontal stretching and shrinking of graphs of functions. In other words, horizontal scaling of functions. To understand what this means, we will take a look at our first example here, which says given y equal to f of x, draw y equal to f of 2x. So this function is very different from this function where you multiply 2 outside f of x. In this case, you are doing a vertical stretching of the function by 2 because every point's y coordinate is doubling. But in this case, you are multiplying 2 with the independent variable, the x itself. So the 2 is being multiplied inside the function, and this is actually one of the trickiest cases of function transformations, but it's actually very easy to understand if once again we think of functions as machines. So here's our function f of x. Let's think of it as a machine which takes some input to produce some output, and let's imagine that for some input x naught, this machine produces the output y naught. Now, what I want you to think about is what will this input output pair x naught y naught transform for this new function f of 2x? What will this pair transform to for this new function? And it's actually fairly straightforward if you think of the function as, if you imagine what this function is doing, what it's really doing is it's first doubling that input and then applying the function f to produce the output. So to produce the same output y naught, what do you think the input should be? The input has to change to produce the same output y naught, and the input simply needs to be x naught by 2 because the input is first being doubled and then the function is being applied on top. So x naught by 2 goes into this machine, and therefore we will get y naught, and this tells us that the original input output pair x naught comma y naught is transforming to the new input output pair x naught by 2 comma y naught. Now, because this could be a bit confusing, let me show you with some specific examples what I mean here. So let's take this point over here, the point that has the x coordinate 6 and a y coordinate of minus 3. So this input output pair for the original function is 6 comma minus 3, which means that for an input of 6, the output is minus 3. Now, for this new function, what input will produce the same output minus 3? What will you have to feed into this new function so that it still outputs the same value minus 3? You will have to input half of this original input. So the original input is 6. So if you half that and take 3, then you feed 3 into this function, you should still get the output minus 3. And therefore, this point over here should transform to the new point 3 comma minus 3, which is this point over here. So this point should move over here. Now let's take some other example. Let's take this point here, which is minus 6 comma minus 4. So that's our original output pair. Now once again, think about what the input needs to be to produce the same output minus 4 for this new function f of 2x. The input needs to be half of minus 6 or minus 3 to produce the same output minus 4. So this point here, minus 6 comma minus 4, will move to this new point minus 3 comma minus 4. So it will come closer to the y-axis. Same thing is happening here. This point is coming closer to the y-axis. And then if you look at this point over here, 8 comma 0, that's our original input output pair. Now what input will produce the same output 0? You take half of this input, or 4. So feed 4 into this new function f of 2x, that will give you the same output 0. So this point 8 comma 0 will transform to this new point 4 comma 0. So every point on the original graph, its x coordinate, the transform point will have half the x coordinate of the original point, and that's what's really going on here. And what that means is that there will be a horizontal shrinking of the original function because all points are coming closer to the y-axis, because the transform points have x coordinates that are half the value, half the corresponding value of the original point. So what does that look like? In this case, it looks something like this. So this is the original function f of x, and this is the transformed function f of 2x. And you can see the for specific examples that we discussed, like this point 8 comma 0 is moving to this point 4 comma 0, and look at this point 6 comma minus 3 is moving to 3 comma minus 3 over here on the new function, and look at this point here, minus 4 comma 0 is moving to minus 2 comma 0. 0 comma 0 stays where it is, of course it does. And you can also look at this point over here, which looks like minus 6 comma minus 4 is moving to minus 3 comma minus 4. So there is a horizontal shrinking of the original function by a factor of 2, and that's what's going on here. So this case is, once again, it's a bit confusing. So if you've still not fully understood it, maybe pause the video for a bit and once again take some specific examples or watch this sequence again to fully understand what I described here. Now let's do the other case where instead of multiplying the variable by some constant greater than 1, you are multiplying it with some constant less than 1. So if your original function is f of x, in this case you need to draw the transformed function f of 1/3 x. So once again, think of functions as machines. Your original function f, let's say for some input x naught, it produces some output y naught. The new function, which is f of 1/3 x, for what value of the input will it produce the same output y naught? What value of the input will you need to feed into this function to produce the same value y naught? In this case, what the machine is doing is it is first multiplying the input by 1/3 and then applying the function. So to get the same output, you should actually triple your input. So you feed in 3 x naught, that becomes 1/3, so x naught, and then the function is applied on top, and therefore you should get y naught. So what that means in terms of the graph is that every point, let any point, let's say, which is x naught y naught on the original function will transform to the point 3x naught comma y naught on the transformed function. So the x coordinate will triple, and let's look at some specific examples. So for example, this point here 1 comma 0 will move to this point 3 comma 0, and let's look at this point here, minus 2 comma 0 will move to minus 6 comma 0. And let's take another example, perhaps let's take this point here, minus 1 comma minus 4 will transform to minus 3 comma minus 4. So you can almost visualize a horizontal stretching of the original function, the opposite of what happened in the previous case. And what does that look like? It looks like this. So here's your original function, and then there's a horizontal stretching because every point on the original function is transforming to a new point where the x coordinate is tripling, and that is what really is going on here. So there's a very common confusion here. While you're multiplying with a constant that's less than 1, the effect is a stretching of the original function, and that's simply because, think of it just in terms of the transformation of every point. So x naught y naught is transforming to 3x naught y naught, because now to produce the same output y naught, you need to feed in an input that is 3 times the original input. So that is what happens here, a horizontal stretching of the original function. So let's summarize what we have learned. If you're transforming f of x to f of cx, c is a constant which is greater than 1, then this is effectively a horizontal shrinking of the original graph using a factor of c. And that's because any point x naught y naught on the original graph, let's say this point here, is transforming to the new point that is x naught by c comma y naught. So if c is greater than 1, then you can see that x naught by c will have an absolute value that is smaller than the original absolute value of the original x coordinate, and therefore your new points, your transformed points, will be closer to the y axis. Their x coordinates will be smaller in size, and that's why there's a shrinking that happens using a factor of c. So if c is, let's say, 5, for example, then you have a horizontal shrinking by a factor of 5. So every point gets transformed to a new point that has an x coordinate 1/5 the original x coordinate, and that is what goes on here. And in the other case where you're transforming f of x to f of cx, where c is less than 1, what happens here is a horizontal stretching using a factor of c. Once again, every point x naught y naught is transforming to this new point x naught by c comma y naught, but in this case c is less than 1. So, your x naught by c actually has an absolute value greater than the original x coordinates absolute value. So, therefore, you can see, for example, this point 2 comma 0 is moving to 4 comma 0, and this point here is also moving away from the y axis. So, every point moves away from the y axis. So, if you have points to the right of the y axis, they move further away, points to the left of the y axis move further away. So, there is a horizontal stretching that happens of the original graph. So, that is horizontal stretching and shrinking, and to help you visualize it even better, let me show you a simulation. So, here is a graph of some function f of x, and I can actually plot two different functions here. One is f of some constant times x, c1 times x, where c1 is actually a constant greater than 1, and one is a function that's f of c2 times x, where c2 is a constant that is less than 1, because the reason I've done it this way is I want to look at the two cases differently. So, let's first look at f of c1 times x, where c1 is greater than 1. So, what should happen? So, if I increase the first constant c1, I should see what? I should see a horizontal shrinking of the original graph. So, let us take a look. Yes, as expected, there is a horizontal shrinking of the original graph, as you can see. And now let me move it back to 1, and now I am back on the original graph. So, once again, let us take a look. As I increase my constant, there is a horizontal shrinking of the original graph. This point stays where it is, but then everything else is coming closer to the y axis. And now let us do the other case, f of c2 times x, where c2 is a constant less than 1. Right now it is equal to 1. So, I see the original graph, but now let me decrease it. So, I should see a horizontal stretching of the original graph. Let us look at that. And yes, as expected, I can see a horizontal stretching that happens, and you could go all the way up to 0, and I'll leave it to you as an exercise to figure out what happens if we go all the way up to 0, but you can clearly see a horizontal stretching that happens in this case. All right, so that's the behavior of horizontal stretching and shrinking. Now let's do a quick couple of questions based on what we have learned. Question number 1 says graph of y equal to cos x is shown over here. It's a periodic function, as you can see, and you might have seen this graph already. And using this graph, we have to plot 2 times cos x, cos 2x, half cos x, cos half x. So, there are a lot of cases mixed here, and the reason I have done it this way is so that we can contrast the different cases. 2 times cos x, so you are multiplying the function with a constant. So, that should be a vertical stretching of the original function. We will take a look at it in a minute. Cos 2x should be what? So, in this case, you are multiplying the variable itself with a constant that is greater than 1. So, this should be a horizontal shrinking of the original function. What about half cos x? In this case, you are multiplying the function with a constant less than 1. So, this should be a vertical shrinking of the original function. And cos half of x, you are multiplying the variable with a constant, the variable x with a constant that is less than 1. So, this should be a horizontal stretching of the original graph. So, let us take a look at all the solutions. So, this is the case where y equal to twice cos of x. So, the curve in white is the original graph, the curve in blue dotted curve is 2 cos x, and you can clearly see a vertical stretching that has happened by a factor of 2. In this case, cos 2x, so you are multiplying the variable by a factor of 2. So, this should be a horizontal shrinking, and yes, we can see that the white curve is the original curve and this curve is shrinking. So, everything is coming together. Every point's x coordinate on the original graph is transforming to a new point with half the original x coordinate, and therefore, you see a horizontal shrinking by a factor of 2. In this case, y equal to half cos x, you are multiplying the function with a constant that is less than 1. So, you can clearly see a vertical shrinking that has happened by a factor of half, and then in this case cos half of x, you're multiplying the variable by a factor of half, and here you can see a horizontal stretching of the original graph by a factor using a factor of half, or the stretch factor is 2, the reciprocal of half. All right, so that's question number 1, and then here is another question. The graph of f of x is shown below, and using this we have to draw the graph of minus 2 f of minus half x plus 1. Now this here looks very complicated, so we'll have to actually break it down step by step into a number of different transitions to see how we are going to arrive at this final function. So what I'll do here is, first I will plot from f of x, I will plot f of minus x, and what should this be? This should simply be a reflection of the original graph about the y-axis. Then I will change x to x by 2, so that will give me f of minus x by 2, and that should be a horizontal stretching by a factor of 2 or using a factor of half. So I've gone up till here, f of minus x by 2, but I need to land here. I need minus half x plus 1 inside. So how do I get this 1 here? So the trick here is you need to modify this expression a little bit to configure it or to express it in terms of translations. So in this case, minus half x plus 1 can be written as minus half times x minus 2. So if you now open the brackets, you will get minus half x plus 1. Now, and this therefore tells me what I need to do here. Once I have f of minus x by 2, I can change x to x minus 2, and that would be a delayed function by 2 units. So if I change x to x minus 2, what I'll get in the next step is f of minus, instead of x I write x minus 2, and then I have a 2 below, and if I open this bracket, I'll instantly get minus half x plus 1, which I need, and then I can just double this and then reflect it about the x axis. So maybe first I double it to get 2f times this is minus half x plus 1, and then in the last step I will multiply it by minus 1, and that will give me minus 2 f of minus half x plus 1. So that's the last step I really need. So how many transformations do we need to do here? 1 from f of x to f of minus x, then 2, and this is a horizontal stretching, then 3, this is a delay, then 4, this is a vertical stretching, and then 5, this is a reflection about the x axis. So quite a number of steps involved, but you can see how logical it is. If you break this down into its component transformations, it actually becomes very easy. So let's now take a look at what this is going to look like. So first, step 1, I am modifying f of x to f of minus x, transforming to f of minus x. So that is a reflection about the y-axis to get f of minus x. Then I am modifying or transforming f of minus x to f of minus x by 2. So that is a horizontal stretching of the function by a factor of 2 or using a factor of half, and that gives me f of minus x by 2. Then in step 3, I modify f of minus x by 2 to f of minus, instead of x I write x minus 2 by 2, and therefore once I open this bracket, that gives me f of 1 minus x by 2. So this transformation is simply a delay of 2 units. You can see here the original function f of minus x by 2, you delay it by 2 units and you get this function over here. And then in the next step, you modify this to twice of this thing, twice of the same thing. So that is a vertical stretching. So this is my function, original function. I am vertically stretching it by a factor of 2 to get twice f of 1 minus x by 2. And then in my last step, I am transforming this to the negative of this, negative of the same thing. And what is that? You take this function and then you reflect it about the x axis, and that gives you minus 2 f of 1 minus x by 2, which is the function we desire. So 5 transformations in total. and therefore this might seem a bit complicated, but it's very, very logical if you're able to analyze the component transformations of this expression. So that concludes our lesson on horizontal stretching and shrinking. I hope you understand this concept. I hope you liked it. This is a bit tricky and many students find it tough. So if you did not fully understand it, no problem. You can go through it again. And yes, I'm sure you will understand it. Let me know what you think in the comments. Thank you.